You are literally surrounded by them right now. There's one in your pocket, probably one on your desk, maybe even one on your wrist. They are the silent, hidden power source for our entire modern world. But what is a battery really doing? Come on, let's take a look inside the amazing chemical machine that makes everything work. Just think about it for a second. A car engine, right? It roars to life by burning fuel. A giant power plant spins a turbine. But a battery, it just sits there, totally silent. It delivers energy without a single moving part. It's a completely different kind of machine, one that works on a level we can't even see. And that's the big question we're going to unpack. How does this little static box manage to power your entire digital life? Well, the answer isn't magic. It's chemistry. And trust me, it's absolutely fascinating. All right, so first things first, let's just clear up the biggest misconception about batteries. They don't actually store electricity. Nope, they store potential energy in the form of chemicals, all ready to be converted into electricity the exact moment you need it. So you can think of it like a chemical powerhouse, just waiting for the signal to go.
And that signal? That happens the moment you turn something on. Whether it's your phone or a flashlight, you are completing a circuit. And the battery's one and only job is to create the push that gets electrons moving through that circuit. And that flow of electrons, well, that's what we call electricity.
So how in the world does it create that push? Well, to see that, we have to look inside. You see, every single battery, from the tiny one in your watch to the massive one in an electric car, is built around three fundamental components. Let's meet the key players. First up, we've got the anode. This is the negative terminal, and you can just think of it as the starting line for the race. It's made of a material that is super generous with its electrons. I mean, it practically wants to get rid of them.
And on the other side, we have the cathode, the positive terminal. This is the finish line. The cathode is made from a material that is, let's say, electron-hungry. It desperately wants to accept the very same electrons that the anode is trying to give away. And this chemical desire, this wanting, that's what creates the potential for power.
And connecting them right in the middle is the electrolyte. Now, this is where it gets really interesting. The electrolyte is this special substance that, and get this, does not let electrons pass through it. It's like a bouncer at a club. Instead, it acts like a shuttle bus just for charged atoms or ions, moving them from one side to the other. This internal flow of ions is the secret ingredient that balances the whole chemical reaction and allows the external flow of electrons to keep on going.
Okay, so we've got our three players in position. The anode wants to give up electrons, the cathode is ready to take them, and the electrolyte is standing by to balance the whole thing out. Now, let's unleash the power. The instant you turn on your device, you give those electrons an external pathway, a wire, a circuit board, whatever. And they rush from the negative anode through all your device's components and right into the welcoming arms of the positive cathode. That organized rush of electrons, that is the electric current that powers your world.
So if current is the flow of electrons, then what's voltage? Well, think of voltage as the pressure behind that flow. Imagine a water pipe. Current is how much water is flowing, but voltage is the water pressure that's forcing it along. It's the measure of how desperately those electrons want to escape the anode and get to the cathode. For a typical AA battery, that chemical push is about 1.5 volts.
But now, let's look at the battery in your phone. A lithium-ion battery has a much stronger chemical desire to move its electrons. Its voltage is around 3.7 volts. That means the electrons are being pushed with more than twice the pressure as in an alkaline battery, which is exactly why we can have such powerful and compact devices today. And this brings us to what is maybe the most important takeaway of this entire thing. Seriously, if you remember just one thing, make it this. A battery is not a tiny tank of electricity. It's a precisely arranged chemical system that's designed to create electricity on demand, right from the potential energy stored in its chemical bombs. Okay, that's all great. But if a battery works by using up its chemical arrangement, how can we possibly recharge it? This is where the real magic of modern batteries comes in. It all comes down to one simple question. Can that chemical reaction be run in reverse? See, a disposable battery is like a one-way street. The chemical reaction that makes electricity permanently changes the materials inside. It's a done deal. But a rechargeable battery, like the lithium-ion in your phone, is built for a two-way reaction. The chemistry can actually be undone. So, and this is so important, when you plug your phone in, you are not filling it up with electricity like you'd fill a bucket with water. No way. You're using an external power source to literally force the electrons to flow backward, which in turn pushes the ions inside the electrolyte back to where they started. You are chemically resetting the entire machine back to its high-energy, ready-to-go state.
Now, thinking about it this way, as a chemical machine, suddenly helps us understand our everyday experiences with batteries. Like, why do they drain faster in the cold? Or why don't they last forever? Let's connect the science to real life.
So, a battery's capacity? That's just how much of that reactive chemical fuel it has packed inside. Temperature affects the speed of those chemical reactions. Cold slows them way down, making the batteries seem weaker, while extreme heat can speed them up too much and cause permanent damage. Then there's internal resistance, which basically means as a battery gets older, it gets less efficient. More energy is wasted as heat instead of doing useful work. It's why an old phone might get warm and not last as long. And that battery management system, it's the unsung hero, a tiny computer that acts like a bodyguard, protecting the battery from overcharging or draining too much, which is absolutely critical for keeping lithium-ion batteries safe and making them last.
Which brings us to the final question. We always say a battery dies, or it ran out of juice. But what has it actually run out of? I mean, it hasn't run out of electrons, right? The atoms and electrons are all still there.
A dead battery is really just a battery where the chemical reaction has hit a stalemate. The anode has given up all the electrons it can, and the cathode has taken all it can hold. That chemical push, the voltage, has dropped so low that it can no longer force a current through your device. All the materials are still inside, they're just not in a useful arrangement to produce power anymore.
So the next time you power something on, just remember what's really happening. You're not just flipping a switch, you're kicking off a tiny, silent, and perfectly controlled chemical reaction. You're watching a brilliant little machine turn pure chemistry into the energy that powers our lives.